you very much. So I'm going to switch a gear a little bit and then talk about the measuring the distance of the universe. Introduction, a while ago, I had a chance to attend a meeting in Honolulu, Hawaii. And the meeting was, the first day of the meeting starts at like 9 a.m. And I woke up very early in the morning, like 7:30 a.m. or something like that. And then I had some time before the meeting starts. So I thought I was going to go out for jogging. So I opened a map of the universe. Doesn't open the map of the universe. Okay, open. So I opened a map of the universe. My hotel was here, and there's a nice beach here. It's Waikiki Beach. So I thought I would run to Kapilani Park around here. And I estimate, so now I use my human distance estimate to estimate a distance from here to here, and it's probably 10 to the minus 13 per sec. So that means I can probably use 30 minutes or something to go there. So I started running. It was okay to get there. And then on my way back, but I thought I'm going to take I was running out of time, so I thought I'm going to take a shortcut. Then somewhere I got lost, and I went this way. And then I looked like this. So a lesson here is measuring a distance of the universe is very important. So today I want to propose a new distance measure using the CO luminosity, molecular line luminosity, and then FWH line width of correlation. Using this correlation, I want to propose a new distance measure. I start with the middle introduction. Dark energy, as you probably know, dark energy is one of the biggest mysteries of the modern astronomy and physics. And it takes 70% of the energy budget of the universe. Nobel Prize in 2011. I think the next key question is the dark energy time variable or constant, or cosmological constant? If you write down the dark energy equation of state, W parameter, as pressure divided by density, if your parameter is like this, then, so this is a constant part, and then if there's this part, this time variable part or not, in this case it's a WZ parameter. And then of course if this part is 0, and then this constant is -1, that's Einstein's cosmological constant. And let's look at the state of the art at the moment. So this is the W0, the constant part in front, and this is the time variable first, WZ. And then the current constraints more or less look like this. And then we have a pretty good understanding on W0, maybe plus minus 10% or so. But in terms of the variability for WZ, we have a large uncertainty. So we want to constrain the time variability of the dark energy. But because this is time variability, one way to figure this out is to go to higher redshift. Because we want a larger time span. Instead of studying it in a local universe at a short time period, we can use the age of the universe and then to take advantage and then investigate the variability. Here's a schematic view. So this is a redshift. This is 0, so it's a local. So this is distant universe. And then this is the normalized distance modulus. So it's normalized Hubble diagram distance modulus. And then so various models are plotted in red and blue here. And as you can see, so those three time variable models, you can see WZ is not 0. So those two WZ is 0, so constant. And then, as you expect, at higher redshift, these time variable models have larger differences because it's a variability. If you have longer time span, it's easier to measure. And then just a reminder, but those gray points are the supernova data points which discovered dark energy and then received the Nobel Prize. And then well, they did a very deep observation, but they are still most of the data are redshift 1 or closer. So we want to plot for this area higher redshift. And then type 1a supernova, which receive the Nobel Prize, are less useful at higher redshift because A, it's too faint to be observed at high redshift. Even type 1 supernova, minus 19th magnitude, but even with the largest telescope in the world today, it's very difficult to observe it beyond redshift 2 or so. Because especially it is difficult to use spectroscopy to measure the redshift and also classify the type of the supernova. So it's very difficult to go higher redshift with type 1a supernova. And also, more fundamentally, type 1, the current theoretical understanding of type 1a supernova is a white dwarf binary, and a white dwarf accretes mass from a companion star. And when it reaches a Chandrasekhar mass, it explodes. And the Chandrasekhar mass is more or less constant, so it's a standard candle, it's a constant brightness. But to accrete a Chandrasekhar mass from a companion star takes time, and it takes few gigayears of time. So that means when the age of the universe is less than a few gigayears, which is the case at higher redshift, this is not going to happen. So there will be few type 1a supernova at a very high T I want to plot. So that's our problem. So we need a brighter and a standard candle. Brighter standard candle available at high T. So instead of type 1a supernova, we need something bigger and stable, something like standard campfire. So what can be a standard campfire? One thing we focused in this work is submillimeter galaxies. Submillimeter galaxies are being observed at very high redshift, which thanks to the new telescope ALMA in Chile. This is a new radio telescope interferometer in Chile. And then this ALMA telescope has been observing many submillimeter galaxies at very high redshift. So these are some example observations from ALMA. And these submillimeter galaxies are clearly detected, and in some cases, the rotation curves, like those rainbow type shape, are observed. And to my very surprise, these are at very, very high redshift, redshift 6 and 5.7. These are very, very high redshift. Okay, so what we did is we collected large sample of CO galaxies we compiled from the literature. So we went to visit the literature and then collected the sample of about 200 galaxies detected in CO emission line, molecular line. And then these 200 galaxies are the largest sample at redshift 2, greater than 2. And then we confirmed the luminosity, CO luminosity, and then line width correlation. So here is the line width of the CO line, and then this is the luminosity of the CO line. And it seems there seems to be a positive correlation. Let's look at it in more detail. Okay, by the way, these people are claimed with a fewer sample, but we confirmed with a much larger number of galaxies.
Is your line 10 higher or supernova with 10?
Because these galaxies are much brighter than the supernova. Supernova is minus 19 magnitude. These galaxies are minus 24 or something like that. So 1,000 times brighter. That's why I know. Thanks for a good question. So this black line is a best fit power level. And then best fit parameter is something like this. And then if you look at the slope, a positive slope of 8 sigma is found. And then those blue lines are connecting median and intervening, and then as you can see, it's increasing. And then if you look at the correlation coefficient, the correlation itself is not so big, but the p-value is very, very small. So it's very significant. So I think we can say correlation is weak, but significant. The scatter, another thing important to mention is the scatter around the best hit line, around this black line, is 43%. And this is consistent with what you expect from the randomly oriented disk. So suppose these spiral galaxies, Thank you. And then their orientation is random. Then you expect 45%, something like scatter, something like this. And this correlation is not very surprising because at lower redshift, from all days, we know the Tully-Fisher relation. When you Tully-Fisher relation is about the brightness of spiral galaxies. This is brighter in astronomy. The smaller numbers, smaller numbers are brighter. Has a good correlation with the rotational velocity of spiral galaxies. This is involved. So in this way, the galaxies are rotating faster, and this is brighter, and this is tight correlation. And this is well-known relation, and people have been using it for cosmology to measure Hubble parameters in local universe since 1970. So I think our relation, CEO luminosity and Randolph relation, can be considered high redshift, distant version of the Tully-Fisher relation. And an important thing is if the relation evolved with redshift or not. So I divided the sample into above redshift 3 in red, and below redshift 3 in blue, and then fit the lines separately. So the red samples are greater than redshift 3, and then blue ones are nearby samples. And then as far as our data can tell, it's almost identical. Consistent to each other within, I should say, consistent to each other within the error. So there's no sign of redshift diversion. If there's no redshift diversion, we can assume this correlation, take it as an assumption, and then use it to measure the distance of the universe. Here's how it works. So we can measure the line with the FWHM. We can just do observation, detect the line, and then measure the width. We can measure it. And then we assume this correlation. So then within this correlation, we can measure the estimate of intrinsic luminosity here. If it's here, it's here. If it's the measurement here, it's here. And then by comparing the assumed intrinsic luminosity to the observed brightness, you can get the luminosity distance. You know the intrinsic luminosity, so if the observation is faint, it's far away. The observation is bright, it's closer, right? And that way we measure the distance and create a Hubble diagram. So here, as a function of redshift, and then this is the luminosity distance. So the distance I measured the way I explained in the previous slide. And then our data points are these. So the red and then these blue points, black and red points are my data points. And then these are the different cosmological models. And then these small points are supernova points. So at the moment, the scatter are a little bit too large to tell difference of which cosmological models are more appropriate. But this at least show potential of the method. And these errors are largely from the observation, and it's going to shrink in the next few years. The reason is because of the ALMA telescope I mentioned earlier. So the number of objects in that plot will increase significantly in the next few years because it's very easy to make these observations with ALMA. For example, redshift 6.5, 3 meters, deep continuum source, it only takes 2.5 seconds to detect with ALMA telescope. So if the random noise, we can beat statistically. And then also, the scatter, large scatter I mentioned was from inclination to the galaxy has orientation, right? But ALMA also can, ALMA spatial resolution in 110 out in 0.037 seconds. And that corresponds to 0.2 kilo per second as I said. And then estimate previously measured size of those galaxies at several kilo per second. So if you have spatial resolution of 0.2 kilo per second, we can resolve these galaxies and determine orientation and then correct it. And that's going to significantly reduce the error. So I wrap up here. So we compiled the largest sample of some of the galaxies with CO detection, about 200, average greater than 2. And then we confirmed weak but very significant CO lines and then luminosity correlation. And then we propose to use this correlation for cosmology to redshift 6 and beyond. And then more details in this. Thank you, organizers, and thank you, everyone.
Just to clarify your statement, so you definitely observe non-zero correlation, but then when the absolute value of the correlation you have large error.
Yes.
You're getting this, and that's the problem. But you're definitely observing correlation.
I believe so. For the correlation,
you have a high p-value, a very good p-value for observing non-zero correlation, but then the absolute value is right now has a big error.
Yes.
How far in redshift do you really have to go to measure the time? Because early on,
so actually, you don't need to go to redshift all the way to 6. Somewhere around here, already difference is large enough. So redshift something like 2-ish is already good enough. And then the observation is much easier here. Or I mentioned redshift 6 for impact, but it's easier to do a more accurate measurement here. That's probably more suitable.
there you probably have to change.
Yeah.